let's talk about let's talk about projectile motion, which is same as the free fall motion. Okay, it's kind of important to understand some terminologies for this. So let's say we bury the cannon inside the ground, and we just let the muzzle stick out, just the opening of the cannon stick out of the ground, right? And then we fire this thing, okay, at this initial velocity v naught. So this v naught is known as the initial velocity, or otherwise known as the muzzle velocity. Right? That's the speed of the bullet coming out of the muzzle of the gun. Okay? That's what V naught is. And this is the initial angle. Okay? This is the initial angle. And that's pretty crucial, what angle you should fire this thing. We're going to consider, right, up direction to be positive and down direction to be negative. And we're also going to consider to the right is positive, right? And to the left is negative. So we have to establish the direction when we start this. This V naught, or the initial velocity, can be broken up into its horizontal and vertical components. The horizontal component can also be represented as VIX or VX naught. VX naught or VIX is equal to basically V naught, which is the initial velocity or the muzzle velocity, times the cosine of the theta naught. The vertical velocity, or VIY, is equal to V naught times sine of theta naught. These are the first things you should always find whenever you do projectile motion. Okay? So what happens when you fire this thing at an angle? Well, the projectile, soon as it's launched, is going to be influenced by gravitational pull of the Earth towards the center. And because gravity always sucks everything towards the center of the Earth, it will actually be influenced vertically only. Okay? But horizontally, there's nothing influencing this horizontally because we are shooting this in a vacuum, so there's no air resistance, there's no headwind or tailwind or crosswind to influence my horizontal velocity. However, vertically, it would always accelerate because of gravity towards the center of the Earth at negative 9.8 meters per second squared. And this influence will happen on the way up as well as on the way down. Okay? So doesn't matter. Okay? When you were to fire this thing, Since horizontally there's nothing influencing this, this initial velocity that we calculate right here will be same for all horizontal velocities at any time. It will not slow down or speed up horizontally. So once it is fired, it would remain at this speed horizontally throughout the whole trajectory. However, because gravity will pull this thing and influence it vertically, your vertical velocity on the way up will slow down, slow down, slow down to zero at maximum height. Okay? So here, this will be positive, this will be positive. Here, my Vy at maximum height will be zero. Okay? So my Vy max will be zero, okay, at maximum Y position. However, I still have horizontal velocity there. And even though this thing is stopped instantaneously vertically, right, for vertical motion, my gravity will still be acting on this particle. Therefore, the acceleration at that point will be still negative 9.8 meters per second squared. Then it turns into negative velocity for the Y velocities because it's going down. And it would increase in speed on the way down in Y direction because of acceleration due to gravity. Okay? So this would be the maximum height. This will be delta x, which is x final minus the x initial. If we start from 0 initial in the x position, right, my delta x is just x final, which is here. This x final is also known as the range. This is different range than what we are used to in math class. In math class, range was the y and domain was the x. No, this has nothing to do with it. It has nothing to do with that. This range, like, shooting range, right? Driving range, like homeowner range. No, that's a little different. Range is just the horizontal distance the projectile travels. Okay, like shooting range or driving range, right? That range is horizontal distance. Okay? If you were to observe this motion in two different angles, for example, let's say we are really high up on cloud number 19 and looking down from the above. Here's my eyeball. That's my eyeball. I'm looking down from really high up, right, of this motion. This will not look any different than if I were to just roll a ball across the ground at that speed. This little up and down will not even factor into my observation whatsoever. It's going to look nothing different than if I were to just roll the ball across the ground at this initial VIX. Does that make sense? And if I were to look at it from this angle, from very, very far away, like looking at it this way, this motion itself would not look anything different than if I were to throw something straight up and then comes back down. This horizontal motion would be negligible looking at it from really far away. It's going to look like whoop. All right. So the independence of the motion that you see from where you are observing, right, is very important. The X motion doesn't really care about what Y motion is doing, and Y motion doesn't really care about what X motion is doing. Only common variable they both use is the time. We could only see this parabola if you were to look at it from this angle, the z-axis, this way, okay, that we can see the parabola. All right? So, here's some assumptions that we can make. Particle is a point particle, which means we don't have to worry about, like, if you were to shoot an elephant out of this cannon, we don't have to worry about elephants' ears flopping around, the tails waggling, and all 4 feet are just like spread out. We don't have to worry about that. We will treat that elephant as a point particle where all the mass of that elephant is concentrated in one singular point and is traveling like that as a point particle. So we don't have to worry about the rotation of the elephant with the trunk flaring out, right? We don't have to worry about the ears rotating and flopping around, right? Since it is done in a vacuum, there's no air resistance or the wind. No tailwind, no headwind, no crosswind, no air resistance, because it's done in the vacuum, all right? That's why the acceleration in the x direction is 0. All right. So acceleration in the x is 0 meters per second squared x hat. However, the acceleration caused by the gravity is always going to be negative 9.8 meters per second squared in the y direction. On Earth. On Earth. On the moon, it will have different value, like negative 1.7. On Mars, negative 3.9. So they will have different values on different planets. All right. Jupiter, I think, is like negative 11 or something. But right now, if we're going to do everything on Earth. All right, so it's negative 9.8. When you work these problems out, you should always separate your x direction and y direction and split them up. Okay? And when you split up the x direction, acceleration in the x is 0. Right? It's good to know. This is really equation number 2. Right? And since we know the acceleration in the x is 0, the whole equation number 2 just boils down to just this. Okay. Now, if you say in your initial x is 0, you could pretty much figure out exact horizontal location if you just know the time and the initial velocity in x. And this is your equation 1. And since acceleration in the x is 0, your final velocity in x will always be your initial velocity in x. All right? So there it is. Initial velocity in x will always be the same for any x velocity at any time, because this does not depend on time. Horizontally, we're done. Vertically, acceleration in the y direction is negative 9.8 meters per second squared. This is equation number 2. However, this doesn't go to 0. It is negative 9.8 meters per second squared. So here, negative 9.8. And similarly, my first equation doesn't go to 0 either for acceleration. So my VFY will change depending on time. All right. Any questions so far? All right. So let's take a look at your homework packet. I'm going to assign your homework right now because we're not going to meet on Wednesday. I would like you to do up to and including page 9 for your homework. Okay? Up to and including. So page 8 and page 9 can be slightly challenging, slightly, for those of you who are very smart. Some of you, it may be challenging. All right, so I give you plenty of clue here, so make sure you can actually do all this. Let's take a look at page 4 on your homework packet. Okay. And projectile motion, free fall motion. So this is a good example that we can do after what we just talked about as firing things at an angle. This is my initial angle theta, which is theta naught, and that happens to be 60 degrees, okay? And this is my initial velocity, or the muzzle velocity, V naught. This right here is my initial position, y initial is 0, and so is the x initial. I guess you could say x initial is also 0. This is your V naught, and this is your theta naught. So if we were to look at this, okay, our V naught is this. My VIX is that, and my VIY is this. Okay. So VIX and VIY should be calculated. So my VIX is really nothing more than V naught, right? Cosine theta naught. Therefore, my VIX is equal to 30 meters per second times cosine of 60 degrees. So my VIX is equal to 15 meters per second, obviously in the x direction, x hat. My VIY, maybe I should put the vector notations in there. Okay. My VIY is V naught sine theta naught, and that is 30 times sine of 60 degrees. So my VIY comes out to 26 meters per second y hat. So these are very good things to know. So that's the first thing you should always do and calculate these VIX and VIY before you even start the problem. Okay, so you know that this thing will travel in a parabolic path and land here on the other side, where your y final is 0 your x final is basically the range. Okay. All right. So let's take a look at A. A, calculate the total time of flight. So let's calculate how much time it takes to do the whole flight. To calculate time, about 95% of the times, use the y direction. Okay? Because we know few things in the y direction that is implicit. So we're looking for time. We know my VIY is equal to 26.0 meters per second. We know A sub y is equal to negative 9.8 meters per second squared. We also know delta y is equal to 0 because it starts at 0 and it finishes at 0. So delta y is y final minus y initial. So 0 minus 0 is 0. Okay? So if we use equation number 2 for the y direction, my delta y is equal to VIYT plus 1/2 A sub yt squared. So we plug in the values. 0 is equal to VIY 26t plus 1/2 times negative 9.8 times t squared. To solve for t, 0 is equal to, I'm going to factor out a t, it'd be 26.0 minus 4.9t. So t is either equal to 0, if I put t is 0, this doesn't matter what this is, it's going to go to 0, or negative 26 over negative 4.9, which comes out to, right, 5.3 seconds. If you don't see how I got this, come and see me after school. We'll have a nice long talk. Now, this makes perfect sense. Why? At t is equal to 0, my position of y is 0. At 5.3 seconds later, my position y is also 0. Therefore, total time of flight is 5.3 seconds, obviously not 0. All right? So that's done. What about part B? Well, at part B, what is the projectile's velocity at the highest point? So at the highest point, right here, my velocity in the y direction is 0, and I only have velocity in the x direction. So this is Vx. So the velocity at the highest point, so part B, Vf at y max is equal to, right, simply Vf x hat, right, plus Vf y hat. Well, we know Vfy hat goes to 0. So Vf at y max is equal to Vfx will always remain 15 meters per second no matter what time it is. So this is just simply 15 x hat plus Vfy is 0 y hat meters per second. So that's how fast it is moving at the highest point. What about part C? For part C, what is the acceleration of the projectile at the highest point? Well, the acceleration vector will always be the same no matter what. That is ax x hat plus ay y hat. We already know the acceleration in the x direction is 0. And we already know ay will always be negative 9.8 towards the center of the Earth. So my acceleration vector will always be 0x hat plus negative 9.8 meters per second y hat. At any point, not just maximum height, but at any point. Any questions so far? All right. And then for part D, they're asking, what is the magnitude of the velocity 3 seconds into the flight? Well, 3 seconds at this here at the halfway point will be half of this, which is like 2.65 seconds. So 3 seconds would be beyond the halfway point, so it should be on the way down. So everybody okay with that logic? All right. So for part D, I know my projectile will be on the way down. Okay, so it'll be like sort of like on the way down, like this. So here, I will have VFX, right, when t is equal to 3 seconds, and I will have my VFY at t is equal to 3 seconds. So this would be my VF, right? And this would be the angle theta. All right? Liam, watch your mouth. Dropping the S-bomb. You're being recorded. All right, so VFX. We don't even have to calculate the VFX. Why? Because we always know it's always going to be the VIX that we already calculated, because it's not going to change. Therefore, it's always going to be 15 meters per second, no matter what time it is, in the x direction. So that's easy. However, your VFY will change because it depends on time, which is VIY plus A sub y t. So your VFY is equal to your VIY, which is 26, minus 9.8 t, right? I guess we could have put t in there already. The t itself is 3 seconds. Right? So my VFY is equal to, okay, negative 3.4 meters per second. So my VF, when t is equal to 3 seconds, is equal to, right, simply 15 x hat, right, minus 3.4 y hat meters per second. So the magnitude of my VF when t is equal to 3 seconds is equal to square root of, you know, the rest, right? 15 squared plus 3.4 squared. And if you work it out, your VF magnitude comes out to 15.4 meters per second as the magnitude. Then the theta is equal to tan inverse of, right, tan inverse of VFY over VFX. Therefore, theta is equal to tan inverse of VFY, negative 3.4, VFX, 15. So theta comes out to negative 12.8 degrees. And that makes perfect sense. It should be on the way down, so it's going to be below the horizontal axis. So my VF at 3 seconds is going to be 15.4 meters per second, comma, theta is equal to negative 12.8 degrees. All right. Any questions? All righty. So I've already done one of the homework problems for you guys. So you're welcome. All right. The rest you need to do on your own. All right, let's take a look at a special case. This is a special case for the flat earthers. All right. Those of you who are believers of flat earth, this problem is for you. All right. We're going to assume the earth is flat, and when we're going to fire this thing, right, we start at 0 height and it ends up at 0 height so that my delta y is 0. Okay? I know the flat earthers are celebrating right now because of this problem. Okay? But this is a very special case. Very, very special case, if you know what I mean. All right? So again, we're given V naught, which is the muzzle velocity, shot at an angle of theta naught, which is the initial launch angle. All right? So we should be able to calculate the VIX, right? The VIX, which is V naught cosine theta. And the VIY is equal to V naught sine theta. Okay? And this R is simply delta X, right? Which is just the X final if we were to keep the initial position X0. Okay? So here, we start at 0 height. So Y initial is equal to 0. And so is the Y final, right? Y final is also equal to 0. So therefore, delta Y is equal to 0. There's no change in height. All right? So these conditions must be true. We're going to also assume that A sub y is equal to just g, which is equal to negative 9.8 meters per second squared. And this is where the confusion happens. So don't follow this. This should be plus, plus, minus, plus, minus, minus, minus. You have to have those in there. So I don't know what happened, but Doc put these negatives in there for some reason. And if you stick in negative 9.8, things just go a little bit crazy. So follow me with my side of the explanation rather than looking at this for right now. So if we were to use the second equation for the y-axis, for the vertical motion, my delta y is equal to VIYT plus 1/2, right? a sub y t squared. Okay? Well, if we were to say my delta y is 0, therefore I'm going to set this equal to 0, and my VIY is V naught sine theta times t plus 1/2 gt squared. I'm going to factor out the time t, just like we did before. Then I get V naught sine theta plus 1/2 gt. You know the time has to go either 0 or t is equal to, right? 0 or, bring this to the other side of a 0, other equal sign, and you get negative, right? V naught sine theta over 1/2 g. So I'm going to put the 2 on the top and g at the bottom. So this is time. Now, if you don't know how I got this, come and see me after school. We'll have a nice long talk. All right? So this time can be now used in the second equation for the horizontal axis. So equation number 2, my delta x is equal to VIXT, right, plus 1/2 a sub x t squared. But we know the acceleration in the horizontal direction is 0. So this whole term just goes to 0. So the only thing we have left is delta x is equal to, right, VIX times time. We know VIX is V naught cosine theta. So we can substitute that in there. All right? So delta x, which is r, is equal to, right, V naught cosine theta times time, which we will substitute that with this. So we're going to substitute that time in here, and we'll get 2 V naught sine theta naught over negative g. I put the negative down at the bottom. I guess this should also be theta naught. Okay, theta naught, theta naught. Therefore, if I multiply the top out, what I'll get is V naught squared times 2 sine theta naught cosine theta naught, whole thing over negative g. There's a trig identity of this. Sine of 2 theta is equal to 2 sine theta cosine theta. It's a double angle theorem. So using this trig identity, we will substitute this 2 sine theta cosine theta as sine of 2 theta. So my range now becomes, right, V naught squared times sine of 2 theta naught, whole thing over negative g. This is known as the range formula. Again, g, right, g is equal to negative 9.8 meters per second squared. When I plug in that negative 9.8 into my g, this negative times this negative 9.8 will become positive. Okay? So let's analyze this John right here. This 2 sine of 2 theta, right? If we were to look at that sine of 2 theta naught, and if we look at the sine function, Sine will have maximum value of 1 at what angle? Yes, Ben?
45 degrees.
Well, at 90 will be maximum of 1.
Oh, I thought you meant for
For, yeah, for, therefore, this theta has to be 45 in order to make that into 90, right? So because sine function has maximum of 1 at 90, this theta has to be 45 degrees to give right? So the theta naught has to be 45 degrees to give the maximum range. Now you can conquer the world, right? So this range formula really is brilliant, actually, right? I mean, assuming there's no headwinds and crosswinds and tailwinds, and this gives you a good estimate of where your cannonballs or artillery is going to land. All right. So if you were to work as an artillery and you're calculating how you should attack, if you want to go over the wall, you want to go higher than 45 degrees. If you want to go through the wall, you want to go lower than 45 degrees. If you want to go for the maximum range, you want to go for 45 degrees. So at 45 degrees, you will get the maximum range, right? So your projectile will go the maximum range at 45 degrees. However, at lower than that, let's say like 30 degrees, let's say you do 30 degrees. At 30 degrees, it will not go as far. 15 degrees, even less, okay? If you go higher than 45, let's say like 60 degrees, it will definitely go higher than 45, but not as far as 45. Matter of fact, it'll go same as 30, the complementary angle. And if you're going 75 degrees, it will go even higher than 60, but not as far as my 60. And of course, 0 degrees will remain at 0 right here. And then 90 degrees will just go straight up and come back down, so it'd be 0 degrees. 0 meters in the range. Everybody okay with that? So do not use this range equation unless you know it is a special case of a flat earthers, right? Only when your delta y is 0, you can use this range equation. So don't use it every time. All right? So what happens when we don't have a flat earth and we're shooting something from high above a cliff? Well, there's always a classic problem. If you were to fire a gun horizontally and drop a bullet from the same height of the gun at the same time when the gun is fired, which bullet will hit the ground first? Anybody know? If you fire a gun horizontally and you drop a bullet from the same height when the gun is fired simultaneously, which bullet, the one dropped or the one that's shot horizontally, which one will hit the ground first? It's a classic problem. Umar?
Do they fall at the same time?
Yeah, they would hit the ground at exactly the same time because both bullets, whether it's fired horizontally or just dropped, will be influenced by gravity exactly the same vertically. So that is correct. All right. So when you're dropping something, right, when you're dropping something, your horizontal Vx is 0 and your Viy is also 0. When you're shooting something horizontally, this has to be horizontally. You cannot shoot it at an angle. If you shoot it at an angle, it doesn't become the same thing anymore. Right? When you're shooting something horizontally, that means your theta naught is equal to 0 degrees. In this case, your Viy is 0, but your Vix is not 0. Okay? So when you were to shoot this thing horizontally, right, and drop something exactly at the same height, they will both be influenced by gravity exactly the same vertically, so they would actually fall at exactly the same rate. Okay? So this is very important that it has to be shot at perfectly horizontal at 0 degrees. Okay? The acceleration in the y direction will be both negative 9.8 meters per second squared for both. And the acceleration for the horizontal direction will be 0 for both. Okay? Therefore, both right? Okay? Whether you shoot it at 10 meters per second horizontally, or 100 meters per second horizontally, or 1,000 meters per second horizontally, they will both hit the ground at the same time, assuming the earth is perfectly flat. Okay? So the horizontal velocity doesn't matter. It just travels further horizontally if you were shooting at a higher speed, but it will still hit the ground at the same time. Now, back in World War II, however, when they shot this 16-inch howitzers, they were missing their targets because they forgot to calculate the curvature of the earth, because the projectile went further than 25 miles. So the horizon is only like 18 miles. And engineers were calculating the range with flat earth equation, and they were missing their targets. But as soon as they calculated the curvature of the earth they were pretty deadly accurate. All right. So horizontal velocity, when it's fired with a greater speed, it will just go further horizontally before it hits the ground, but they will still both hit the ground at the exact same time. So I put this video link of Mythbusters, and you can take a look at it. It's on the Schoology notes folder. I won't see you guys until Friday because Wednesday, I guess, is in-service day for teachers, so you guys are free, right? So do your homework, watch the video, and if you're stuck, go take a look at Khan Academy. I think Sal's pretty good at explaining things. All right, any questions? I think we're done for today. All right.